Every spacecraft humanity has ever sent to Jupiter was designed to die there. Juno, Galileo, Voyager, not one carried the capability to return. This wasn't a matter of budget or will. It was physics admitting defeat. The fuel required to escape Jupiter's gravity and claw your way back to Earth exceeds what any chemical rocket can provide. The propellant mass needed would outweigh every rocket ever launched. Combined, we celebrate these one-way arrivals while quietly ignoring the arithmetic that traps us in the inner solar system. Getting to Jupiter is hard. Coming home is impossible. This is the story of the mathematics that makes Jupiter a prison. We will explore the energy debt that compounds beyond payment and reveal why round-trip missions may remain forever beyond our reach. If you want to understand what the laws of the universe truly forbid, hit that like button and subscribe. And also, I want to know where you are watching from. Let me know in the comment section. Settle in. What you're about to hear will change how you see that bright dot in the night sky forever. Let's begin. The distance to Jupiter seems almost reasonable when you first encounter it. 365 million miles at closest approach. Roughly 480 million on average. Numbers large enough to impress but small enough to calculate. Your brain can process 400 million. You can write it down. You can divide it by spacecraft velocities and arrive at travel times measured in years, not centuries. Jupiter appears to sit just beyond Mars, a logical next step in humanity's outward expansion. We reached the Moon in 3 days. We can reach Mars in 7 months. Jupiter should simply require a longer version of the same journey. This thinking has shaped 60 years of space exploration planning. Mission designers sketched trajectories to Jupiter using the same fundamental principles that carried astronauts to the lunar surface. The math works on paper. Spacecraft depart Earth, coast through the void, and arrive at the gas giant with fuel to spare. Juno reached Jupiter in 2016 after a 5-year journey. Galileo arrived in 1995 following a 6-year odyssey. The Voyager probes flew past in 1979, their flybys lasting mere hours, but their data revolutionized our understanding of the outer solar system. Every successful mission reinforces a powerful, seductive illusion. Jupiter is reachable. Humans have sent robots there repeatedly. The technical challenges appear manageable. The timeline seems acceptable. A crewed mission, in crude theory, would simply require scaling up existing capabilities. More supplies, better radiation shielding. The fundamental approach remains unchanged from Apollo. This optimism, however, conceals a mathematical catastrophe hiding in plain sight. The spacecraft that reached Jupiter share one critical feature that mission summaries rarely emphasize in their triumphant press releases. Juno will eventually plunge into Jupiter's atmosphere, intentionally destroyed to prevent contamination of potentially habitable moons. Galileo met the same fate in 2003 after 8 years of orbital operations. The Voyagers continued past Jupiter toward interstellar space, never to return. Pioneer 10 and 11 sailed through the Jovian system and kept going, their trajectories carrying them forever away from Earth. These were not round-trip missions. They were one-way tickets dressed up as exploration successes. The celebration of arrival obscured the impossibility of return. Understanding why requires examining the physics of interplanetary travel with uncomfortable, unflinching precision. Every journey through space obeys laws that cannot be negotiated, appealed, or circumvented through clever engineering. Orbital mechanics operates with the mathematical certainty of geometry. When you launch a spacecraft from Earth toward Jupiter, you are not pointing a vessel at a destination and flying in a straight line. You are manipulating gravitational relationships between worlds in constant motion around a star that itself hurtles through the galaxy. Earth orbits the Sun at approximately 67,000 miles per hour. Jupiter orbits at roughly 29,000 miles per hour. Both planets trace elliptical paths that bring them closer together and farther apart in cycles lasting just over a year. The distance between the two worlds varies by hundreds of millions of miles, depending on where each planet sits in its orbit. Launch timing matters enormously. A spacecraft departing when the planets are at opposition can reach Jupiter in under 3 years. A spacecraft departing at unfavorable times might require 5 years or more, burning additional fuel to compensate for the geometric disadvantage. Your spacecraft must escape Earth's gravity, enter an orbit around the Sun that intersects Jupiter's position months or years later. Every maneuver costs propellant, every course correction depletes reserves. The void offers no refueling stations, no supply depots, no second chances if you miscalculate the fuel budget. The most efficient path from Earth to Jupiter follows what physicists call a Hohmann transfer orbit, named after the German engineer Walter Hollmann, who described it mathematically in 1925. This trajectory uses minimum fuel by accepting maximum time. The spacecraft launches from Earth and enters an elliptical orbit around the Sun, with its closest point near Earth's orbit and its farthest point near Jupiter's orbit. The vessel then coasts along this path for roughly 30 months. Engines, silent momentum carrying it outward. Hohmann understood something fundamental about orbital mechanics that escapes casual observation. You cannot simply point at Jupiter and accelerate until you arrive. Instead, you fall along curved paths, dictated by the Sun's gravity, climbing uphill away from the Sun as you travel outward, losing speed as gravitational potential energy replaces kinetic energy. The transfer orbit represents a carefully calculated fall that begins near Earth and ends near Jupiter, with the spacecraft arriving at precisely the moment Jupiter passes through that point in space. The timing requirements create launch windows that open briefly and close for over a year. Miss the window and mission planners face uncomfortable choices. Wait 13 months for the next opportunity, or launch anyway and pay a fuel penalty that might double the propellant requirements, or accept a longer transit time that extends crew exposure to radiation and increases the burden on life support systems. This patience, or lack thereof, has a price measured in a quantity called delta V. Delta V represents the total change in velocity a spacecraft must achieve throughout its mission. Every acceleration and deceleration contributes to this budget. Think of it as the currency of space travel, the fundamental unit that determines what missions are possible and what missions remain forever out of reach. You cannot borrow delta V. You cannot earn it along the way except through gravity assists. You must carry every unit from the launch pad in the form of propellant that will be burned and expelled into the void. The delta V required to reach low Earth orbit from the surface measures approximately 9.5 kilometers per second. That single number explains why rockets look the way they do. The payload, the actual spacecraft or satellite being delivered to orbit, represents a tiny fraction of the launch mass. The violence required to achieve orbital velocity consumes almost everything the rocket carries. From low Earth orbit, the delta V to escape Earth's gravitational influence and enter a transfer trajectory toward Jupiter adds roughly 6 kilometers per second. This trans-Jupiter injection burn must occur at precisely the right moment when the spacecraft's orbital position aligns with the desired departure trajectory. The burn typically lasts several minutes, consuming tons of propellant while accelerating the spacecraft to roughly 42,000 kilometers per hour relative to Earth. After injection, the spacecraft coasts. For 30 months, it falls outward along the transfer ellipse, engines silent, propellant preserved for later mission phases. The area maneuvers during this cruise involve small course corrections to refine the trajectory burns measured in meters per second rather than kilometers. The spacecraft crosses the orbit of Mars roughly 8 months after departure. It continues outward through the asteroid belt, past the orbits of countless rocky bodies that never coalesced into planets. Month after month, the Sun shrinks in the rear-view windows while Jupiter grows slowly ahead. Arrival at Jupiter requires another expenditure of delta V. The spacecraft approaches at roughly 6 kilometers per second relative to Jupiter's motion. Without intervention, it would fly past in a hyperbolic trajectory, gaining a gravity assist but never entering orbit. Capturing into orbit demands a burn that slows the spacecraft enough for Jupiter's gravity to trap it on a closed elliptical path. This orbital insertion burn represents a critical mission phase where failure means total loss. The spacecraft executes the maneuver autonomously because light-speed communication delays prevent real-time control from Earth. At Jupiter's average distance, radio signals take roughly 43 minutes to reach Earth. A round-trip communication spanning 86 minutes precludes any meaningful intervention during a burn lasting 10 or 15 minutes. The spacecraft's computers must handle contingencies without human input. Mission planners have refined these calculations over decades. A minimum energy transfer to Jupiter requires roughly 17 to 18 kilometers per second of total delta V from Earth's surface to Jovian orbit. This figure includes the climb to Earth orbit, the trans-Jupiter injection, cruise corrections, and orbital insertion. It represents the theoretical floor, the absolute minimum velocity change needed to make the outbound journey. 17 kilometers per second. The figure seems almost modest compared to the velocities involved in space travel. Light travels at 300,000 kilometers per second. Jupiter orbits at 13 kilometers per second relative to the Sun. 17 kilometers per second of delta V to cross 400 million miles appears efficient, even elegant, but the elegance conceals violence. 17 kilometers per second represents roughly 20 times the speed of a rifle bullet. Achieving this velocity change requires burning tens of thousands of kilograms of propellant through rocket engines operating at temperatures exceeding 3,000 degrees Celsius. The rockets that launch toward Jupiter do not gently accelerate. They detonate controlled explosions continuously for minutes at a time, converting chemical energy into thrust with brutal efficiency. Every kilogram of payload bound for Jupiter demands roughly 50 kilograms of fuel and rocket structure to escape Earth. This ratio, known as the mass fraction, governs all chemical rocketry. The relationship emerges from fundamental physics, encoded in the Tsiolkovsky rocket equation, a formula derived in 1897 that has constrained space exploration ever since. The rocket equation reveals an exponential relationship between delta V and mass. Doubling your payload does not merely double your rocket, it might quadruple the launch mass. Tripling the payload can increase launch mass by a factor of 8 or more. The relationship curves upward without mercy, punishing ambition with mathematical certainty. The Saturn V rocket that carried astronauts to the Moon stood 363 feet tall and weighed 6.5 million pounds, fully fueled. It delivered roughly 140,000 kilograms to low Earth orbit. The ratio between launch mass and orbital payload exceeded 20 to 1. That ratio reflects the delta V cost of reaching orbit and nothing more. The Moon sits a mere 250,000 miles away. Jupiter lies roughly 2,000 times farther. Gravity assists offer an apparent escape from this tyranny. By flying close to planets along the journey, spacecraft can steal orbital energy from those worlds, gaining velocity without burning fuel. The technique exploits a loophole in conservation of momentum that allows small objects to borrow speed from massive ones. The planet barely notices the exchange. The spacecraft gains velocity that would otherwise require tons of additional propellant. The physics of gravity assists seems almost magical until you understand the mechanism. When a spacecraft approaches a planet from behind relative to the planet's orbital motion, it falls into the planet's gravitational influence, accelerates toward the planet, swings around, and exits with more velocity than it entered. The planet loses an infinitesimal fraction of its orbital momentum, slowing by an amount far too small to measure. The spacecraft gains that momentum, emerging from the encounter faster than it arrived. The Galileo mission to Jupiter used gravity assists from Venus and Earth to gain the speed needed for its outbound journey. Launched in 1989 aboard Space Shuttle Atlantis, the spacecraft first flew inward toward Venus, gaining velocity from a close passage in February 1990. It then returned to Earth's vicinity twice, in December 1990 and December 1992, picking up additional speed with each flyby. Only after this years-long series of gravitational boosts did Galileo finally head outward toward Jupiter, arriving in December 1995. The maneuver added years to the transit time but saved thousands of kilograms of propellant. Without gravity assists, Galileo would have required a much larger rocket or a much smaller scientific payload. The technique has become standard practice for outer solar system exploration. Voyager 2 used gravitational slingshots around Jupiter, Saturn, and Uranus to reach Neptune in 1989. The Cassini mission to Saturn required 7 years of gravity assists involving Venus twice, Earth once, and Jupiter once. New Horizons used Jupiter to cut years off its transit time to Pluto. Each mission demonstrates that clever trajectory design can partially offset the punishing mathematics of the rocket equation. but gravity assists carry hidden costs that mission summaries rarely mention. Each planetary flyby adds years to mission duration. The spacecraft must reach the assisting planet when it occupies the correct position for the desired trajectory change. This requirement constrains launch windows severely. The Galileo trajectory worked only because Venus, Earth, and Jupiter occupied specific positions in 1989 that would not repeat for decades. Missing the launch window would have meant redesigning the entire mission. 4 robotic missions with operational lifespans measured in decades, trading time for fuel, works beautifully. Spacecraft do not age in the biological sense. They do not consume food or oxygen during the long cruise. They simply coast. Their systems powered by radioisotope generators or solar panels, waiting for the next planetary encounter. 6 years of transit presents no fundamental obstacle for a machine designed to operate for decades. For crewed missions, the calculus shifts dramatically. Astronauts age during transit. They consume resources continuously. They require air, water, food, and meaningful activity every day of the journey. They accumulate radiation damage from cosmic rays that stream through interplanetary space at velocities approaching the speed of light. Every additional year in space increases the burden on life support systems and decreases the probability of crew survival. Time, which is a free resource for robots, becomes a precious and dangerous commodity for humans. The Juno spacecraft exemplifies the current state of Jupiter exploration. Launched in 2011, it arrived in 2016 after a 5-year cruise that included an Earth gravity assist. The probe entered a highly elliptical polar orbit around Jupiter, sweeping close to the cloud tops every 53 days before retreating to regions where radiation intensity dropped to survivable levels for its electronic systems. Juno's orbit was carefully designed to minimize radiation exposure while maximizing scientific return. Jupiter's magnetic field traps charged particles in intense radiation belts that dwarf Earth's Van Allen belts by orders of magnitude. The radiation would destroy unshielded electronics within hours. By diving close to the planet beneath the most intense radiation zones and then retreating rapidly, Juno could gather data while limiting cumulative damage. The spacecraft carries its most sensitive electronics in a titanium radiation vault weighing approximately 180 kilograms. This shielding reduces radiation dose to internal components by roughly 800 times. Even with this protection, engineers expected progressive degradation throughout the mission. Some instruments would fail, some systems would weaken. The spacecraft that completed the mission would be less capable than the spacecraft that began it. Juno carries no return capability whatsoever. Its orbital insertion burn consumed a substantial portion of remaining propellant. The spacecraft lacks the fuel to escape Jupiter's gravity, even if operators wanted to retrieve it. When its mission ends, controllers will command a deorbit burn that sends the spacecraft into Jupiter's atmosphere at roughly 100,000 miles per hour. This planned destruction prevents any possibility of the spacecraft contaminating Europa or other potentially habitable moons with Earth microbes that might have survived the journey. Planetary protection protocols require that spacecraft without adequate sterilization avoid contact with potentially life-bearing worlds. Juno was never sterilized for landing on such worlds because landing was never part of the mission design, but the destruction is also an inevitability disguised as a precaution. Juno cannot come home because coming home requires energy the spacecraft does not have and could not carry. The propellant budget was calculated years before launch, accounting for every maneuver the mission would require. Return was never included in those calculations because return was never possible. Here lies the mathematical trap that swallows round-trip mission planning. The delta-V budget for reaching Jupiter represents only the opening bet in a game where the final stakes exceed your initial investment by enormous margins. You spend 17 kilometers per second to arrive. You then face a return journey that demands additional energy drawn from reserves that have already been depleted by arrival itself. The outbound illusion persists because we celebrate arrivals without questioning departures. Every Jupiter mission press release emphasizes the achievement of reaching the gas giant. Journalists write about technical challenges overcome, years of planning validated, scientific discoveries awaiting. Television coverage shows jubilant engineers in mission control as confirmation of orbital insertion arrives after anxious minutes of waiting. The story ends with success. Few mention the unstated corollary: nothing we send there will ever return. The one-way nature of these expeditions hides in the gap between engineering reality and public perception. We have mastered the art of reaching Jupiter. We have not begun to solve the problem of leaving it. Consider what a round-trip mission would actually require. Launch from Earth and begin the outbound transfer. Coast for approximately 30 months while Jupiter and Earth trace their separate orbits around the Sun. Arrive at Jupiter and perform orbital insertion burns that consume significant propellant. Conduct whatever operations the mission requires while waiting for orbital mechanics to align a return window. Depart Jupiter using propellant reserves calculated years earlier and now depleted by arrival burns. Operational maneuvers and storage losses. Coast another 30 months on the inbound transfer. Perform Earth capture burns using whatever propellant remains. The round trip requires a minimum of 5 to 6 years under optimal conditions. This timeline assumes perfect launch windows which occur roughly every 13 months for both outbound and return trajectories. Missed a window and the delta V penalty might add 20% to fuel requirements. Mystery besmews that moves a mission becomes impossible without additional propellant that does not exist aboard the spacecraft. Miss a window entirely and you wait another 13 months while your spacecraft consumes resources in orbit around Jupiter. The hostile radiation environment degrades systems continuously. Electronic components accumulate damage from particle bombardment. Mechanical systems fatigue from thermal cycling between Jupiter's shadow and direct sunlight. Cryogenic propellants warm gradually despite insulation, eventually boiling away into space. The clock runs in only one direction while waiting for orbital mechanics to permit departure. The spacecraft that arrives at Jupiter cannot simply refuel. No tankers orbit the gas giant. No propellant depots await visiting ships. No infrastructure exists to support operations beyond what each spacecraft carries. The isolation is absolute. The self-sufficiency must be complete. Every gram of propellant needed for a return must travel from Earth across 500 million miles of void. The outbound journey to Jupiter represents a promissory note written against the future. The spacecraft that departs Earth carries propellant calculated to arrive at Jupiter with reserves for orbital insertion and operations. Return propellant must also be carried, adding mass that itself requires more propellant to lift from Earth. The debt compounds before the spacecraft even leaves the launch pad. The debt comes due when you try to come home. The interest rate is set not by banks or governments, but by the gravitational constant of the universe itself. Jupiter's gravity well waits at the end of every trajectory, ready to collect what physics demands. The illusion of accessibility persists because we have successfully paid the outbound fare repeatedly. Robots have reached Jupiter and conducted operations that transformed our understanding of the outer solar system. Humans could theoretically survive the transit with sufficient radiation shielding and life support. The distance, while vast, falls within technological reach using propulsion systems that already exist. These facts create false confidence that round-trip missions represent merely a scaling problem rather than something more fundamental. We built bigger rockets to reach the moon. We can build bigger rockets to reach Jupiter. The logic seems unassailable until you examine what awaits at the destination. Jupiter is not a slightly harder version of the moon. It is not a more distant version of Mars. It is a qualitatively different challenge that bends the rocket equation toward numbers that strain credibility. The planet that served as destination becomes something else entirely once you arrive. Its gravity well captures everything that benches close, demanding payment in delta V that interplanetary travelers struggle to afford. The journey there seems possible only because we have been measuring half the problem. The outbound illusion endures because we have never attempted the other half. The round-trip orbital energy debt begins accumulating from the moment of launch and continues growing through every mission phase. What that debt totals when you finally try to leave Jupiter reveals why every spacecraft we send arrives as an explorer and remains as a prisoner. Jupiter contains more mass than every other planet in our solar system combined. Saturn, Uranus, Neptune, Earth, Venus, Mars, Mercury, and all the dwarf planets and asteroids and moons could be gathered together, and Jupiter would still outweigh them. The gas giant tips the scales at roughly 1.9 times 10 to the 27th kilograms. Written in standard notation, this number requires 28 digits. Written in words, it defies comprehension. Jupiter masses approximately 318 times Earth. It would take over 1,000 Jupiters to equal the Sun's mass. Yet, this single planet dominates everything else in the solar system that is not the Sun itself. This mass shapes the architecture of the outer solar system in ways both obvious and subtle. Jupiter's gravity deflects comets that would otherwise strike the inner planets, acting as a cosmic shield that may have allowed life on Earth to develop without constant bombardment. Over billions of years, Jupiter has captured asteroids into stable orbital families that trace paths 60 degrees ahead of and behind the planet in its orbit. These Trojan asteroids number in the hundreds of thousands, held in gravitational equilibrium by Jupiter's influence on the shape of space itself. Jupiter tugs on the orbits of its own moons with such force that tidal heating melts their interiors. Io, the innermost of the 4 Galilean satellites, experiences gravitational flexing that generates more volcanic activity than anywhere else in the solar system. Hundreds of active volcanoes dot Io's surface, erupting continuously, resurfacing the moon so rapidly that impact craters cannot accumulate. Europa's subsurface ocean exists because Jupiter's gravitational kneading generates heat that keeps water liquid beneath kilometers of ice. The potential for life in that dark ocean drives some of humanity's most ambitious exploration planning. When astronomers search for planets around distant stars, they look first for Jupiter-sized bodies because such massive worlds create detectable wobbles in stellar motion. A Jupiter orbiting a Sun-like star causes that star to move in a small circle around the system's center of mass. This motion shifts the star's light through the Doppler effect, revealing the planet's presence across light-years of distance. The technique that discovered the first exoplanets worked precisely because Jupiter-mass worlds create Jupiter-sized gravitational effects. This mass creates a gravitational field of terrifying intensity. Every object with mass attracts every other object with mass. The force depends on both masses involved and decreases with the square of the distance between them. Jupiter's enormous mass means its gravitational pull exceeds that of any other planet at any given distance from its center. Approach Jupiter, and you approach the deepest gravitational well any planet in our solar system can offer. The surface gravity of Jupiter, measured at the altitude where atmospheric pressure equals Earth's sea level pressure, reaches approximately 24.5 meters per second squared. This figure represents roughly 2.5 times Earth's surface gravity. A human standing in Jupiter's upper cloud deck would weigh 2.5 times their Earth weight. A person weighing 150 pounds on Earth would weigh 375 pounds on Jupiter. Every movement would require more than double the effort. Standing would exhaust muscles adapted to Earth conditions. Walking would become a struggle against crushing weight. Running would be impossible. Falling would be catastrophic. These calculations remain purely theoretical because Jupiter has no surface to stand on. There is no boundary between atmosphere and interior, no solid ground beneath the clouds, no bedrock at any depth. The cloud tops the telescope's photograph give way to thickening haze, then to hydrogen compressed into liquid form, then to hydrogen squeezed so intensely that electrons detach from atoms, and the material conducts electricity like metal while remaining fluid. This metallic hydrogen layer extends for tens of thousands of kilometers. Deeper still, a core of heavier elements may exist under pressures millions of times greater than Earth's atmosphere, temperatures hotter than the surface of the Sun. No spacecraft could survive descent into these depths. No material humans have created would withstand the crushing forces. Jupiter's interior remains forever inaccessible to direct exploration. Spacecraft operate far above these hellish regions, orbiting in the relative safety of space, where Jupiter's gravity diminishes with distance but never disappears. The Juno spacecraft traces a highly elliptical path that carries it from roughly 4,200 kilometers above the cloud tops at closest approach to approximately 8 million kilometers at its farthest points. This extreme orbital shape reflects design choices driven by the radiation environment rather than gravitational concerns. Jupiter's magnetic field traps charged particles in belts of radiation that dwarf Earth's Van Allen belts by orders of magnitude. The particle energies and fluxes near Jupiter exceed those anywhere else humans have sent spacecraft. Electronics exposed to this radiation accumulate damage that degrades performance and eventually causes failure. By diving close to the planet beneath the most intense radiation zones and then retreating to safer distances, Juno survives to complete orbit after orbit. The radiation environment around Jupiter deserves particular attention because it compounds every other challenge of operating near the gas giant. Jupiter's magnetic field is the largest structure in the solar system, stretching millions of kilometers into space, its tail extending beyond the orbit of Saturn. This immense magnetosphere traps electrons and protons accelerated to tremendous energies, creating radiation belts that would deliver lethal doses to unshielded humans within minutes at certain altitudes. The inner radiation belt, extending from Jupiter's cloud tops to roughly 3 Jupiter radii, contains the most intense radiation, with particle fluxes millions of times greater than Earth's Van Allen belts. Spacecraft operating within this zone require heavy shielding that adds mass to every system. Juno carries a titanium radiation vault weighing 180 kilograms to protect its most sensitive electronics. Even with this protection, the spacecraft accumulates damage with each close pass, its systems gradually degrading toward eventual failure. A crewed spacecraft would require far more extensive shielding to protect human occupants, adding thousands of kilograms to vehicle mass. This shielding mass requires propellant to transport, compounding the already severe weight penalties that Jupiter missions face. The radiation also affects propellant storage systems. High-energy particles penetrating tank walls can alter the chemistry of stored propellants, potentially degrading performance or creating hazardous compounds. Cryogenic systems face additional challenges as radiation damages insulation materials, increasing heat leak rates and accelerating propellant boil-off. The radiation environment transforms routine spacecraft operations into a continuous battle against an invisible enemy that never relents. The orbital mechanics reveal Jupiter's gravitational power with elegant precision. At closest approach, Juno accelerates to roughly 209,000 kilometers per hour relative to Jupiter's center. The spacecraft covers thousands of kilometers in minutes, whipping past the cloud tops in a blur of data collection before climbing away. At its farthest point, Juno slows to a crawl, taking weeks to traverse the distant arc of its orbit. The difference between these velocities reflects energy exchange with Jupiter's gravitational field. Falling toward the planet converts potential energy to kinetic energy, accelerating the spacecraft as it descends. Climbing away reverses the exchange, converting kinetic energy back to potential energy as the spacecraft slows. The spacecraft rides this gravitational roller coaster indefinitely, trading speed for altitude and altitude for speed in an endless cycle that orbital mechanics dictates. Changing this cycle costs propellant. Every adjustment to the orbit requires burning fuel that cannot be replaced. Raising the closest approach point demands acceleration at the farthest point. Lowering the farthest point demands deceleration at closest approach. Changing the orbital plane to view different latitudes requires burns at specific locations timed to the spacecraft's position. Visiting moons requires trajectory shaping, burns that intercept the moon's orbit at the correct time and place. Mission planners allocate propellant budgets for these maneuvers years before launch, knowing that every kilogram spent on orbital adjustments becomes a kilogram unavailable for other purposes. The accounting is merciless. There are no refunds, no overdrafts, no second chances to recover propellant spent on maneuvers that proved unnecessary. The escape velocity from Jupiter quantifies the gravitational trap's depth with a single number. Escape velocity represents the minimum speed an object must achieve to climb out of a gravitational well and never fall back. Fire a projectile upward at less than escape velocity and it will eventually slow and fall back down regardless of how high it climbs. Fire it at exactly escape velocity and it will climb forever, slowing continuously but never quite stopping, reaching infinite distance with zero remaining velocity. Fire it faster than escape velocity and it will escape with speed to spare, cruising into interplanetary space with leftover kinetic energy that carries it toward other destinations. At Jupiter's cloud tops, escape velocity measures approximately 59.5 kilometers per second. This number dwarfs escape velocities elsewhere in the solar system. Earth's escape velocity from sea level reaches only 11.2 kilometers per second. A spacecraft leaving low Earth orbit needs roughly this velocity relative to Earth's center to break free and coast into interplanetary space. Mars requires only 5 kilometers per second for escape from its surface. The Moon demands just 2.4 kilometers per second. Even Saturn, the solar system's second largest planet with its spectacular rings and dozens of moons, requires only 35.5 kilometers per second for escape from its cloud tops. Jupiter's escape velocity exceeds Earth's by a factor of more than 5. The gas giant's gravitational grip tightens around everything that approaches, demanding energy payments that dwarf those required anywhere else humans might consider visiting. Fortunately, spacecraft need not escape from the cloud tops. They operate in orbits hundreds of thousands or millions of kilometers above the atmosphere, where escape velocities drop substantially with increasing altitude. The relationship follows an inverse square root function that orbital mechanics students learn in introductory courses. Double your distance from Jupiter's center, and escape velocity drops by roughly 30%. Quadruple the distance, and it drops by half. The numbers become progressively less terrifying with altitude. At an orbital altitude of 400,000 kilometers above Jupiter's cloud tops, roughly 470,000 kilometers from the planet's center, escape velocity falls to approximately 23 kilometers per second. At 1 million kilometers from center, it drops to roughly 16 kilometers per second. At 2 million kilometers, approximately 11 kilometers per second. At 3 million kilometers, escape velocity falls to about 9 kilometers per second. Approaching values comparable to Earth escape velocity, the numbers become manageable if you orbit far enough from Jupiter's center. But orbital mechanics introduces a crucial subtlety that transforms these numbers into something more complex. A spacecraft already in orbit around Jupiter possesses orbital velocity that partially counts toward escape. The spacecraft is not starting from rest. It is already moving at significant speed, circling Jupiter in an orbit that required substantial velocity to establish. The delta V required to escape equals the difference between escape velocity and current orbital velocity, not escape velocity itself. Consider a spacecraft in a circular orbit at 1 million kilometers from Jupiter's center. At this distance, orbital velocity measures roughly 11.3 kilometers per second. The spacecraft circles Jupiter at this speed continuously, its velocity vector constantly rotating to keep it on the circular path. Escape velocity from this altitude measures roughly 16 kilometers per second. The delta V required to escape becomes 16 minus 11.3. Approximately 4.7 kilometers per second. The spacecraft need not accelerate from rest to 16 kilometers per second. It must only add 4.7 kilometers per second to its existing velocity, redirecting its circular motion into an escape trajectory. This calculation seems to shrink the problem substantially. 4.7 kilometers per second of delta V sounds almost manageable. Earth's departure from low orbit requires about 3 kilometers per second. Mars' departure from low orbit requires about 2.5 kilometers per second. But this analysis omits a critical factor that mission planners cannot ignore. Escaping Jupiter's gravity represents only part of the challenge facing a return mission. The spacecraft must also reshape its orbit around the Sun to return to Earth. Jupiter orbits the Sun at roughly 13 kilometers per second. A spacecraft that merely escapes Jupiter with minimal velocity finds itself in a heliocentric orbit similar to Jupiter's. Circling the Sun adds Jupiter's distance with no particular tendency to fall inward toward Earth. Returning to Earth requires reducing heliocentric velocity, so the spacecraft falls into an elliptical transfer orbit with its closest point near Earth's orbital distance. The spacecraft must depart Jupiter with a specific velocity and direction relative to both Jupiter and the Sun. The escape burn and the trans-Earth injection combine into a single maneuver that accomplishes both objectives simultaneously. The delta V required for this combined maneuver depends on orbital geometry at departure time, ranging from roughly 5 to 8 kilometers per second from typical Jupiter parking orbits. The lower figure assumes optimal geometry. The higher figure applies when geometry is less favorable, which it often will be given the constraints of return window timing. Add the delta V for Earth capture at journey's end, and the return trip demands roughly 7 to 11 kilometers per second total. depending on trajectory choices and whether error braking at Earth is available. Error braking uses atmospheric drag to slow the spacecraft, reducing or eliminating the propulsive delta V required for capture. Without a roking, the spacecraft must carry propellant for the full capture burn. With a roke raking, the spacecraft must carry a heat shield capable of surviving atmospheric entry at interplanetary velocities. Either choice adds mass to the spacecraft design. These return delta V figures must be compared to the outbound delta V budget. The Part 1 established. The outbound journey from Earth's surface to Jupiter orbit costs roughly 17 to 18 kilometers per second. The return journey costs 7 to 11 kilometers per second from Jupiter orbit back to Earth. The return appears cheaper than the outbound journey in raw delta V terms. 7 is less than 17. The return trip seems like it should be easier. This comparison misleads catastrophically because of where each delta V must be provided. The outbound delta V is supplied by rockets on Earth's surface with full access to launch infrastructure, propellant production facilities, assembly buildings, test ranges, and the entire industrial capacity of human civilization. Thousands of engineers support each launch. Propellant is manufactured in chemical plants and delivered by truck. Rockets are assembled in climate-controlled buildings by trained technicians using precision tools. Any problem discovered during preparation can be addressed before launch. The return delta V must be supplied by rockets at Jupiter using only propellant that travel 400 million miles from Earth. No support infrastructure exists at Jupiter. No propellant production facilities operate there. No technicians can repair malfunctioning hardware. The spacecraft carries everything it needs from Earth, or it does without. Every kilogram of return propellant launched from Earth requires additional mass to lift it from the surface, escape Earth's gravity, cruise to Jupiter, and capture into Jupiter orbit. The mass multiplication begins at Earth's surface and compounds through every mission phase. Consider the cascade of requirements in detail, working backward from Jupiter departure to Earth launch. A spacecraft needs 1,000 kilograms of dry mass to survive the return journey to Earth. This mass includes the crew capsule structure, heat shield for Earth re-entry, life support equipment for the 30-month return transit, navigation and communication systems, power generation, thermal control, and crew provisions. 1,000 kilograms represents an extremely minimal return spacecraft stripped of every gram that mission success does not absolutely require. Real designs would likely require several times this mass. To depart Jupiter and return to Earth requires approximately 8 kilometers per second of delta V from a practical parking orbit, using a middle estimate between optimal and suboptimal geometry. Apply the rocket equation with chemical propulsion at 4.5 kilometers per second exhaust velocity. The required mass ratio equals E raised to the power of 8/4.5, approximately 5.9. The spacecraft must mass 5.9 times as much before the return burns as after. For 1,000 kilograms of dry return mass, the spacecraft needs 5,900 kilograms total mass in Jupiter orbit before the return sequence begins. This means 4,900 kilograms of propellant must be loaded in tanks orbiting Jupiter. Now trace this requirement backward through mission phases. That 5,900 kilogram spacecraft must be delivered to Jupiter orbit from Earth. Jupiter orbital insertion requires 1.5 kilometers per second of delta V to slow the approaching spacecraft enough for Jupiter's gravity to capture it. The mass ratio for this burn equals roughly 1.4. The spacecraft approaching Jupiter must mass 1.4 times what it will mass after insertion. 5,900 kilograms after insertion means 1,860 kilograms approaching Jupiter. The 1,860 kilograms must cruise from Earth to Jupiter over 30 months. Navigation requires occasional trajectory correction maneuvers, small burns that consume perhaps 50 kilograms of propellant over the journey. Add this to the approaching mass, yielding 8,310 kilograms departing Earth vicinity. Trans-Jupiter injection from low Earth orbit requires 6 kilometers per second of delta V. Mass ratio equals E raised to the power of 6/4.5, approximately 3.8. The spacecraft in low Earth orbit before injection must mass 3.8 times the post-injection mass. 310 kilograms after injection means 31,570 kilograms in low Earth orbit. Finally, reaching low Earth orbit from Earth's surface requires 9.5 kilometers per second of delta V. Mass ratio equals E raised to the power of 9.5, 4.5, approximately 8.2. The rocket on the launch pad must mass 8.2 times the orbital payload. 31,578 kilograms in orbit means 258,940 kilograms on the launch pad. Over 250,000 kilograms on the launch pad to deliver 1,000 kilograms of dry mass back to Earth from Jupiter. And this calculation assumes perfect efficiency at every stage. No margins for contingency, no redundancy for critical systems, no allowance for mass growth during development. Real missions require margins of 20 to 30% on every subsystem. Real margins multiply these already enormous numbers further upward. The Saturn V rocket that carried astronauts to the Moon could lift approximately 140,000 kilograms to low Earth orbit, delivering the 31,078 kilograms required for even this minimal Jupiter return mission would consume roughly 1/4 of a Saturn V's orbital capacity. But the Saturn V no longer exists. No rocket currently operational can lift 140,000 kilograms. The largest operational rockets lift roughly 20 to 25,000 kilograms. Multiple launches would be required with orbital assembly, adding complexity, risk, and time during which cryogenic propellants boil away. Scale the calculation to a more realistic return spacecraft. Instead of 1,000 kilograms, assume 5,000 kilograms of dry return, mass still modest, but perhaps minimally adequate for a crewed vehicle with appropriate life support, radiation shielding, and redundancy. The launch mass requirement climbs to roughly 1.3 million kilograms. Over 1 million kilograms on the launch pad for a single Jupiter return mission. 10 Saturn V launches worth of mass, or 50 launches of the largest currently operational rockets. Scale further to include the crew's outbound transit vehicle. The systems required for Jupiter orbital operations. The redundancy that human spaceflight demands, and the margins that prudent engineering requires. Mission masses climb into the millions of kilograms. The numbers exceed any space program's demonstrated capability by factors that make the gap qualitative rather than merely quantitative. NASA recognized these limitations as early as the 1960s. When Apollo's success generated enthusiasm for ever more ambitious missions, studies conducted by NASA centers and aerospace contractors examined crewed missions to Jupiter using nuclear thermal propulsion, which offered higher exhaust velocities than chemical rockets. Even with this advanced technology, the studies concluded that Jupiter return missions required capabilities far beyond anything then available or reasonably projected. The mass requirements, mission durations, radiation exposure, and system reliability demands all exceeded feasible limits. These studies were quietly filed away as the space programs shifted focus to the space shuttle and eventual Mars planning. The conclusions remain valid today, confirmed by subsequent analyses using modern tools and updated assumptions. These calculations explain why no Jupiter mission has ever included return capability. The mass penalty for return is so severe that mission designers exclude it from the trade space before detailed design begins. Every kilogram allocated to return propellant becomes a kilogram unavailable for scientific instruments, communication equipment, power systems, or operational propellant for Jupiter orbit maneuvers. Faced with the choice between a capable one-way mission and an inadequate round-trip attempts, planners choose capability every time. The Galileo mission exemplifies this trade. The spacecraft carried instruments to study Jupiter's atmosphere, magnetic field, and moons. It carried a probe that descended into Jupiter's atmosphere and transmitted data for 57 minutes until crushing pressure destroyed it at a depth of roughly 150 kilometers below the cloud tops. It carried propellant for orbital insertion and 8 years of orbital maneuvers that enabled close passes of Io, Europa, Ganymede, and Callisto. It carried no return capability because return would have consumed mass that instead produced scientific discoveries. Some might wonder whether Jupiter's moons could provide an escape route from the gravity prison. Ganymede, the solar system's largest moon, exceeds Mercury in diameter and possesses its own magnetic field. Its surface gravity measures roughly 1/7 of Earth's, and escape velocity from Ganymede is only 2.7 kilometers per second. Could a spacecraft use Ganymede as a staging point, landing to refuel or transferring to a smaller vehicle optimized for the return journey? The answer illuminates why Jupiter's gravity well functions as a prison rather than merely a difficult destination. Ganymede orbits Jupiter at roughly 1 million kilometers from the planet's center. A spacecraft in Ganymede's vicinity must still escape Jupiter's gravity to return to Earth, and from that distance, Jupiter escape still requires substantial delta V. Landing on Ganymede and returning to orbit consumes additional propellants. No fuel production infrastructure exists on Ganymede, so any propellant used there must still be transported from Earth. The same logic applies to Europa, Io, and Callisto. Each moon offers lower gravity than Jupiter itself, allowing landing and surface operations with reduced propellant costs compared to Jupiter's cloud tops, but none offers escape from Jupiter's gravitational dominion. A spacecraft might tour all 4 Galilean moons, landing on each, collecting samples from each, and still lack the propellant to carry those samples home. The moons orbit within the prison. They do not provide doors out of it. They are fellow prisoners, bound to Jupiter by the same gravitational chains that capture visiting spacecraft. Jupiter's gravity well operates as a prison through economics, as much as physics. The physics permits escape given sufficient propellant. The economics of delivering that propellant from Earth prohibit accumulating sufficient reserves. Each kilogram of return capability costs so much to deliver that mission designers consistently choose to spend those kilograms elsewhere. The gravity well depth creates what might be called a capability cliff. Below certain delta B thresholds, missions remain feasible with sufficient effort and resources. Above those thresholds, missions transition from hard to impractical to effectively impossible. The moon lies well below the cliff. Lunar return requires roughly 2.5 kilometers per second of delta V from lunar orbit. The Apollo missions accomplished this with margins to spare, returning crews safely even when systems malfunctioned. The delta V budget allowed for contingencies that never arose because prudent engineering built in reserves. Mars lies near the base of the cliff. Mars return requires roughly 5 to 7 kilometers per second, depending on mission architecture and use of aerobraking. The numbers stretch chemical propulsion but remain achievable with careful design. Mass ratios climb to roughly 3 or 4 for the return burns. Challenging but demonstrated in operational rocket stages. Mars return missions dominate current human spaceflight planning precisely because the numbers close with foreseeable technology. The cliff has not yet been reached. Jupiter lies near the top of the cliff, perhaps beyond it entirely, for chemical propulsion. The 8 kilometers per second required for return from Jupiter orbit does not merely exceed lunar and Martian requirements by a modest factor. It pushes against the mathematical limits of what chemical propulsion can deliver while carrying meaningful payload. The exponential nature of the rocket equation means that adding 2 or 3 kilometers per second to the delta V requirement does not proportionally increase difficulty. It might make the mission impossible where previously it was merely very hard. This categorical difference means that engineering approaches which worked for Moon and Mars cannot simply scale up to Jupiter. The Apollo spacecraft weighed roughly 30,000 kilograms in lunar orbit before the return burns. A Jupiter return spacecraft would need to be many times larger to carry the propellant required for the higher delta V. But larger spacecraft require more propellant to deliver to Jupiter, which requires more propellant to launch from Earth, which requires larger rockets or more launches. The cascading requirements feed back on themselves, amplifying small increases in return delta V into enormous increases in launch mass. The feedback loop spirals toward infinity as requirements approach the theoretical ceiling of chemical propulsion performance. Human missions would face identical physics. The rocket equation does not care whether cargo or crew rides atop the propellant tanks. It does not relax its demands for human life. It calculates mass ratios with the same precision regardless of mission importance or crew hopes for survival. A crewed spacecraft entering Jupiter orbit would need the same delta V to escape that a robotic spacecraft needs. The difference lies in what that propellant mass means for total mission design. Robotic spacecraft can be optimized for one-way journeys without ethical concerns. They carry instruments, collect data, transmit findings, and accept destruction as the mission's natural end. The engineers who design them and the controllers who operate them feel loss when missions end, but the loss is professional rather than personal. No families mourn. No children grow up without parents. No communities lose members. Crewed spacecraft cannot treat crew death as an acceptable mission outcome. They must carry return capability or acknowledge that the crew will never come home. This requirement transforms Jupiter missions from extraordinarily difficult to potentially impossible. The propellant for crew return must be carried from Earth, multiplied through every mission phase, and delivered to Jupiter orbit, intact and usable after years of interplanetary cruise and months of orbital operations. The crew's survival depends on propellant that has traveled 400 million miles, survived years of storage in the harsh radiation environment, and remains sufficiently pure and pressurized for engine ignition when the time comes. Failure at any point in this chain means crew death. The gravity prison accepts all visitors. It releases none who enter unprepared to pay the gravitational ransom. The ransom calculation must account for more than delta V and mass ratios alone. Time enters the equation through orbital mechanics that dictate when departure becomes possible. The waiting period between arrival and departure creates additional costs that compound the difficulty of return. The prison extracts payment not only in propellant, but in time, and time at Jupiter carries its own devastating price. Orbital mechanics operates on schedules that human planning cannot influence. The planets move according to gravitational laws established when the solar system formed 4.5 billion years ago. These movements create windows of opportunity for interplanetary travel that open briefly and close for months or years. A spacecraft cannot depart for a destination whenever mission controllers choose. It must wait for geometry to permit efficient travel, and a spacecraft cannot return from a destination on demand. It must wait again, sometimes far longer than the outbound wait, for geometry to permit the journey home. This temporal constraint transforms Jupiter missions from difficult to potentially deadly. The waiting period between arrival and departure creates costs that compound the already severe challenges of escaping Jupiter's gravity well. Time becomes an enemy as implacable as gravity itself, extracting payment in degraded systems, depleted resources, and accumulated damage that may render return impossible, even for spacecraft that arrived with theoretical capability to leave. The synodic period between Earth and Jupiter determines when transfer windows occur. This period measures the time between successive alignments of the two planets. As viewed from the Sun, Earth completes one orbit in approximately 365 days. Jupiter requires roughly 4,333 days, nearly 12 Earth years, to complete its much larger orbit. The faster inner planet repeatedly overtakes the slower outer planet, creating alignment opportunities separated by 399 days on average. 399 days, roughly 30 months between windows. Miss one opportunity, and the next lies more than a year in the future. This interval governs both outbound and return trajectories. A spacecraft launching from Earth toward Jupiter must depart during a window lasting a few weeks, when the planetary geometry permits minimum energy transfer. The spacecraft departing Jupiter for Earth faces the same constraint. The windows do not synchronize conveniently. Arriving at Jupiter does not guarantee that a return window stands open. Consider the timing challenge in concrete terms. A spacecraft launches from Earth during an optimal window and begins the 30-month journey to Jupiter. It arrives and performs orbital insertion, successfully entering Jupiter orbit. The return window that would permit minimum energy transfer back to Earth may have closed months before arrival, or it may lie months in the future. The exact timing depends on trajectory details that mission planners calculate years before launch. Minimum energy return trajectories from Jupiter require the spacecraft to depart when Jupiter and Earth occupy specific positions relative to the Sun. The spacecraft must exit Jupiter's gravitational influence with a velocity vector that places it on an elliptical orbit around the Sun, an orbit with its closest point near Earth's orbital distance. This geometry occurs approximately once per synodic period. Between these opportunities, departure either costs substantially more propellant or becomes effectively impossible. Realistic mission architectures assume spacecraft will wait 6 to 18 months in Jupiter orbit before favorable return geometry develops. Some mission studies extend this waiting period even longer to accommodate scientific objectives requiring extended observation time. The Galileo spacecraft operated at Jupiter for 8 years, precisely because return was never planned. Without return propellant to preserve, mission designers could optimize for science rather than departure timing. Crewed missions cannot adopt this approach. Astronauts require continuous life support. They consume oxygen, water, and food every day regardless of what orbital mechanics permits. They generate carbon dioxide that must be scrubbed from cabin air. They produce waste that must be processed or stored. They require thermal regulation, radiation protection, and meaningful activity to maintain psychological health. Every system supporting crew survival draws power, consumes supplies, and accumulates wear. The waiting period subjects all these systems to extended stress they might otherwise avoid. A spacecraft transiting to Jupiter operates its life support for 30 months. A spacecraft waiting at Jupiter for a return window might operate life support for an additional 12 to 18 months. Another 30 months of transit follows. A crewed Jupiter mission might require 7 years of continuous life support operation. Under the most optimistic timeline, 7 years exceeds the operational duration of any crewed spacecraft in history. The International Space Station has operated for over 2 decades, but its crews rotate regularly and it receives resupply missions multiple times per year. A Jupiter-bound spacecraft carries everything it needs from Earth. No resupply is possible. No crew rotation occurs. The systems must function without maintenance from Earth-based technicians, without replacement parts from orbital supply runs, without any support except what the crew can provide using resources they brought with them. But consumable supplies and life support duration represent only part of the waiting period's cost. The more insidious expense involves propellant that slowly disappears while the spacecraft waits for departure geometry. High-performance chemical rockets use cryogenic propellants. Liquid hydrogen and liquid oxygen combust to produce exhaust velocities around 4.5 kilometers per second, substantially better than any storable propellant combination. This performance advantage makes cryogenic propulsion the default choice for high-energy maneuvers like Jupiter escape. Every major rocket upper stage uses hydrogen and oxygen. The Space Shuttle main engines use them. The Saturn V upper stages use them. Any serious Jupiter return mission would use them. Liquid hydrogen exists only at temperatures below -253 degrees Celsius. This temperature lies just 20 degrees above absolute zero, the theoretical minimum where all molecular motion ceases. Liquid oxygen boils at -183 degrees Celsius, warmer than hydrogen, but still far below any temperature occurring naturally in the inner solar system. Maintaining these temperatures in space requires active thermal management that fights against heat leaking in from every direction. The Sun radiates energy that reaches Jupiter's orbit at roughly 50 watts per square meter. This represents only 4% of the solar intensity at Earth's distance, but it still provides continuous heat input to any spacecraft. The spacecraft itself generates heat from electronic systems, crew metabolism, and power generation. This heat must be rejected to space through radiators, but perfect thermal isolation of propellant tanks remains impossible. Heat finds paths through structural connections, through insulation imperfections, through radiation that penetrates reflective coatings. When heat reaches cryogenic propellants, it causes evaporation. Liquid molecules at the surface absorb energy, transition to gas phase, and escape into the vapor space above the liquid. Tank pressure rises as vapor accumulates. If pressure climbs too high, the tank might rupture. Spacecraft designers prevent this by venting excess vapor to space, allowing the gas to escape and carrying its heat energy away from the remaining liquid. This venting represents propellant loss. Every molecule of hydrogen or oxygen that boils off and vents becomes unavailable for engine burns. The propellant supply shrinks continuously, not through use, but through the simple passage of time in an imperfectly insulated environment. Boil-off rates depend on tank design, insulation quality, thermal environment, and operational practices. Modern cryogenic systems in Earth orbit might achieve hydrogen boil-off rates of 1 to 2% of tank contents per month under favorable conditions. Laboratory demonstrations have achieved lower rates for limited periods. But deep space conditions differ from Earth orbit. Jupiter's distance from the Sun reduces solar heating, but does not eliminate it. The extended mission duration exposes insulation to years of micrometeorite impacts, radiation damage, and thermal cycling that degrade performance over time. Assume a well-designed spacecraft achieves 1.5% monthly hydrogen boil-off at Jupiter. This rate falls within the range of current technology, perhaps slightly optimistic for a multi-year mission, but not unreasonably so. Calculate the cumulative loss over a 12-month waiting period. The spacecraft arrives at Jupiter with 50,000 kilograms of liquid hydrogen reserved for the escape and return burns. During the first month of waiting, 1.5% boils away 750 kilograms vented to space as gas. The remaining liquid totals 49,250 kilograms. During the second month, 1.5% of the remaining liquid boils away. The absolute loss decreases slightly because less liquid remains to absorb the incoming heat. 739 kilograms escape. The tank now holds 48,511 kilograms. The pattern continues through subsequent months. Each period sees the same percentage loss applied to a shrinking base. After 6 months, approximately 45,700 kilograms remain. After 12 months, roughly 41,700 kilograms remain. The spacecraft has lost over 16% of its hydrogen simply by existing in Jupiter orbit. 16% sounds almost acceptable until you trace its implications through the rocket equation. The escape burn that originally assumed 50,000 kilograms of hydrogen now must proceed with only 41,700 kilograms. The mass ratio for the burn decreases proportionally. The delta V the spacecraft can achieve falls by roughly 800 meters per second. 800 meters per second of delta V represents the difference between successful escape and permanent capture. It represents the difference between reaching Earth and falling short into a useless heliocentric orbit. It represents the difference between crew survival and crew death. The waiting period consumes this margin without providing any benefit, converting carefully calculated reserves into gas that disperses into the void. Mission planners must compensate for boil-off by loading extra propellant at departure from Earth. If 12 months of waiting will consume 16% of hydrogen reserves, then 16% more hydrogen must be carried initially, but this compensation cascades through the rocket equation. Extra hydrogen at Jupiter requires extra propellant for Jupiter orbital insertion. Extra insertion propellant requires extra propellant for the trans-Jupiter cruise. Extra cruise propellant requires extra propellant for Earth departure. Extra Earth departure propellant requires extra propellant for launch from the surface. Each kilogram of boil-off compensation at Jupiter translates to tens or hundreds of kilograms on the launch pad. A 16% propellant margin at Jupiter might require a 50% increase in total mission mass at launch. The waiting period's thermal cost multiplies through every mission phase, inflating already enormous mass requirements to figures that strain credibility. Zero boil-off technology offers a potential solution. Active refrigeration systems could theoretically remove heat from propellant tanks faster than it enters, maintaining cryogenic temperatures indefinitely without venting. Cryocoolers, using various thermodynamic cycles, have demonstrated the ability to reach liquid hydrogen temperatures in laboratory settings. If such systems could be packaged for spaceflight, the waiting period's propellant cost might be eliminated entirely. But zero boil-off systems carry their own penalties. Cryocoolers require substantial electrical power to operate. Removing the heat that leaks into a large propellant tank demands cooling capacity measured in watts or tens of watts. The power systems to provide this electricity add mass to the spacecraft. At Jupiter's distance from the Sun, solar panels produce only 4% of their Earth orbit output. Generating meaningful power for cryocooler operation requires either enormous solar arrays or nuclear power sources. Radioisotope thermoelectric generators provide reliable power for deep space missions that produce limited output. A modern multi-mission radioisotope thermoelectric generator delivers approximately 110 watts while massing roughly 45 kilograms. Powering cryocoolers for large propellant tanks might require multiple generators, adding hundreds of kilograms to spacecraft mass and consuming plutonium-238 that remains scarce and expensive to produce. Nuclear fission reactors could provide kilowatts of electrical power, but add thousands of kilograms to spacecraft mass. They require heavy shielding to protect crew and sensitive electronics from radiation. They introduce failure modes that could leave the spacecraft without power in the outer solar system, hundreds of millions of miles from any possibility of repair or rescue. Zero boil-off systems have never been demonstrated in operational spaceflight for the durations Jupiter missions require. The technology readiness level for long-duration cryogenic storage in deep space hovers around level 4 or 5 on NASA's 9-point scale. Flight-ready systems require level 8 or 9. The gap between current capability and mission requirement spans decades of development work. Relying on zero boil-off technology for Jupiter return means betting crew lives on engineering that does not yet exist. Storable propellants eliminate boil-off concerns entirely. Monomethyl hydrazine and nitrogen tetroxide remain liquid at room temperature and moderate pressure. They require no insulation, no refrigeration, no thermal management beyond basic spacecraft temperature control. They wait patiently in their tanks for months or years, ready for use whenever engines need to fire. The Galileo spacecraft used storable propellants throughout its 8-year Jupiter mission without propellant loss to evaporation. The penalty for this convenience appears in engine performance. Storable propellants combust at lower temperatures and produce lower exhaust velocities than cryogenic combinations. Monomethyl hydrazine and nitrogen tetroxide engines achieve roughly 3.1 kilometers per second exhaust velocity. The 30% performance gap might seem manageable until the rocket equation amplifies it. For a Jupiter escape requiring 7 kilometers per second of delta V, cryogenic propulsion demands a mass ratio of approximately 4.7. Storable propulsion demands a mass ratio of roughly 9.5. The spacecraft must carry twice as much storable propellant as cryogenic propellant to achieve the same velocity change. But storable propellant is denser and requires lighter tanks, partially offsetting the mass increase. The net penalty reaches roughly 50 to 70% additional propellant mass. This penalty cascades through mission phases just as boil-off compensation does. 50% more propellant at Jupiter requires more propellant for insertion, cruise, and launch. Total mission mass increases substantially. The already severe mass requirements for Jupiter return climb higher still. Some mission designers have proposed hybrid approaches. Storable propellants could provide orbital maneuvering capability at Jupiter, while cryogenic propellants provide the high-performance escape burn. The cryogenic tanks would be sized for immediate use upon arrival, minimizing boil-off exposure. Storable systems would handle the waiting period's operational needs. The approach reduces but does not eliminate the mass penalties of either propellant type. The waiting period degrades more than propellant. Every system aboard the spacecraft experiences wear, fatigue, and accumulating damage during months of operation in Jupiter's hostile environment. Jupiter's magnetic field is the strongest of any planet in the solar system. It traps charged particles, primarily electrons and protons, in radiation belts that dwarf Earth's Van Allen belts. The particle energies and fluxes near Jupiter exceed those anywhere else humans have sent spacecraft. Electronics exposed to this radiation accumulate damage that degrades performance and eventually causes failure. Radiation damage in semiconductors occurs through several mechanisms. High-energy particles passing through silicon create defects in the crystal structure. These defects trap charge carriers, increasing resistance and altering the electrical characteristics of transistors. Over time, threshold voltages shift, leakage currents increase, and circuits that function perfectly at launch begin to malfunction. Memory cells flip unexpectedly. Processors generate errors. Sensors drift out of calibration. Spacecraft designers mitigate radiation damage through shielding, redundancy, and radiation-hardened components. Shielding mass reduces particle flux reaching sensitive electronics. Redundant systems allow switching to backup components when primaries fail. Radiation-hardened chips use design techniques that tolerate higher damage levels before malfunction. These measures extend operational lifetime but cannot prevent degradation entirely. The Galileo spacecraft experienced progressive radiation damage throughout its Jupiter mission. After 8 years, multiple systems had degraded significantly. The tape recorder that stored data between Earth communication sessions partially failed, forcing mission controllers to modify operations around the limitation. Imaging sensors showed increased noise levels. Computer memory accumulated errors that required workaround procedures. The spacecraft remained functional but operated with reduced capability compared to its launch condition. A crewed spacecraft waiting at Jupiter would experience similar degradation. Life support electronics would accumulate radiation damage. Navigation computers would develop increasing error rates. Communication systems would lose sensitivity as receiver components degraded. The spacecraft that departed Jupiter would be less capable than the spacecraft that arrived, even if no component failed completely. Thermal cycling adds mechanical stress that compounds radiation damage. A spacecraft orbiting Jupiter passes repeatedly between direct solar illumination and planetary shadow. Each transit creates a thermal cycle. Surfaces facing the Sun warm substantially. Surfaces facing away cool toward the deep cold of space. The temperature differential across the spacecraft structure creates thermal stresses as materials expand and contract at different rates. A single thermal cycle causes negligible damage. The spacecraft was designed to tolerate the temperature range, but hundreds or thousands of cycles accumulate fatigue in structural joints, adhesive bonds, and mechanical connections. Seals that maintained pressure at launch begin to leak. Deployable mechanisms that operated smoothly develop stiffness or binding. A 12-month waiting period in a 53-day Jupiter orbit exposes the spacecraft to roughly 7 complete orbital cycles. Each orbit includes thermal cycles as the spacecraft passes behind Jupiter. Additional thermal variation occurs as the spacecraft's orientation changes for communication, pointing, scientific observations, and thermal management. The cumulative stress reaches levels that affect long-term reliability. Batteries experience chemical degradation that reduces capacity regardless of charge cycling. The rechargeable batteries that store electrical power for eclipse passages and peak demand periods slowly deteriorate through internal chemical reactions. Electrode materials degrade, electrolytes decompose. The battery that could store 10 kilowatt-hours at launch might store only 8 kilowatt-hours after years of operation. Reduced battery capacity limits operational flexibility and reduces margins for contingency situations. Mechanical systems experience wear even in the absence of atmosphere. Reaction wheels that control spacecraft orientation spin on bearings that gradually develop roughness. Gimbal mechanisms that point engines and antennas accumulate backlash in their gear trains. Valve seats that control propellant flow develop wear patterns that affect sealing. Lubricants migrate, evaporate, or degrade under radiation exposure. The composite effect of all these degradation mechanisms is called aging decay. Mission planners originally developed the concept for expendable launch vehicles that discard stages during ascent. Each stage performs its function and separates, leaving a smaller vehicle to continue. Aging decay describes the reverse process. Systems degrade while waiting, reducing the effective capability of later mission phases. For Jupiter return missions, aging decay means the spacecraft that departs Jupiter will be significantly less capable than the spacecraft that arrived. Propellant reserves will have shrunk from boil-off. Electronics will have accumulated radiation damage. Mechanical systems will have developed wear and fatigue. Batteries will have lost capacity. Thermal control surfaces will have degraded from micrometeorite impacts and ultraviolet exposure. The crew themselves experience degradation during extended spaceflight. Burn density decreases in microgravity at roughly 1 to 2% per month, despite exercise countermeasures. Muscle mass declines. Cardiovascular conditioning deteriorates. Vision changes occur as fluid pressure in the head increases without gravity to draw fluids downward. Immune system function may be compromised. Psychological stress accumulates from isolation, confinement, and distance from Earth. A crew that has spent 30 months traveling to Jupiter then 12 months waiting for a return window, then faces another 30 months of return transit, will be substantially debilitated compared to their launch condition. They will operate a degraded spacecraft with reduced margins using bodies that have lost strength and endurance. The combination of human and mechanical degradation reduces the probability of successful return below levels that responsible mission planners can accept. Some mission architectures attempt to reduce waiting period costs through operational complexity. Pre-positioned return vehicles could arrive at Jupiter years before the crew, waiting unmanned while the crew conducts a faster transit. The crew would arrive, transfer to the waiting return vehicle, and depart during the first available window after arrival. This approach minimizes crew exposure to Jupiter's radiation environment and reduces the life support consumables required. But pre-positioned vehicles experience the same degradation as crewed vehicles. Propellant boils away whether humans are present or not. Radiation damages electronics regardless of crew status. Thermal cycling stresses structures without human observers. The return vehicle that has waited years for crew arrival may have degraded below reliable operation thresholds. Crew survival depends on systems that have operated unmanned in a hostile environment for longer than any deep space mission has ever demonstrated. Pre-positioning also requires that 2 complete spacecraft systems reach Jupiter successfully. The return vehicle must launch years before the crew, survive interplanetary transit, enter Jupiter orbit, and maintain functionality until crew arrival. Any failure in the pre-positioned vehicle strands the crew with no return capability. If each vehicle has a 90% probability of successful operation, the combined probability of both working falls to 81%. Mission failure rates that would be unacceptable for single-vehicle missions become built into the architecture. Propellant depots represent another proposed mitigation. Instead of carrying all return propellant from Earth, spacecraft could refuel at Jupiter from pre-positioned reserves. Multiple tanker missions would deliver hydrogen and oxygen to Jupiter orbit over several years, accumulating sufficient propellant for a crewed mission return. The depot would use zero boil-off technology to maintain cryogenic storage indefinitely, avoiding the losses that would doom the propellant if stored aboard individual spacecraft. Propellant depots require infrastructure that does not exist. No one has demonstrated long-term cryogenic storage at Jupiter. No one has developed systems for transferring cryogenic propellants between spacecraft in zero gravity. No one has proven zero boil-off technology for the multi-year durations Jupiter depot operation would require. The depot itself becomes a mission of unprecedented complexity that must succeed before crewed missions can even attempt departure from Earth. The cost of establishing Jupiter propellant depot infrastructure would reach tens of billions of dollars before any crewed mission launched. The development timeline would span decades. The technical risks would include challenges that no space program has ever solved. Proposing a depot as a solution to Jupiter return essentially proposes solving an impossible problem by first solving several other impossible problems. The waiting game at Jupiter admits no winning strategy using current technology. You can wait with cryogenic propellants and lose them to boil-off. You can use storable propellants and accept crippling mass penalties that make return impractical. You can pre-position return vehicles and accept reliability penalties that make crew survival a gamble. You can propose propellant depots and accept development costs and timelines that no space agency can sustain. Every approach leads to the same conclusion. Time at Jupiter erodes the margin needed for return. The spacecraft that arrives theoretically capable of escaping Jupiter's gravity well becomes progressively less capable through the simple passage of time. The round-trip orbital energy debt includes a temporal component that accrues continuously from the moment of arrival. Interest accumulates in lost propellant, degraded systems, reduced crew capability, and narrowing margins for successful return. Orbital mechanics sets the waiting period with absolute authority. The planets will be where the planets will be. No amount of human preference changes the geometry of return windows. Physics sets the interest rate on the temporal debt without negotiation. Propellants will boil, systems will degrade, crews will weaken. These processes continue at rates determined by chemistry, radiation flux, and human physiology, indifferent to mission schedules and crew hopes. The waiting game reveals that Jupiter mission difficulty extends beyond propulsion and mass ratios. Even a spacecraft that somehow arrived with sufficient propellant for return would face months of attrition before departure became possible. The time that must pass between arrival and return extracts costs that may exceed original reserves, transforming theoretical capability into practical impossibility. The mathematics of this impossibility invites examination. The rocket equation, the boil-off rates, the degradation functions, the delta-V requirements all combine into a system of constraints that mission planners have studied for decades. The results of those studies consistently indicate that Jupiter return lies beyond current capability. Understanding why requires examining the arithmetic in detail, tracing the numbers through every mission phase to see exactly where the boundaries of possibility lie. The Tsiolkovsky rocket equation governs all of rocketry with the authority of mathematical law. Derived in 1897 by Konstantin Tsiolkovsky, a self-taught Russian schoolteacher working in provincial obscurity, the equation describes the relationship between a rocket's velocity change, its exhaust velocity, and the ratio of its initial mass to final mass. The mathematics requires nothing beyond algebra that secondary school students master. The implications have constrained human ambition in space for over a century. Tsiolkovsky never built a rocket. He never launched anything into space. He worked out the theory of space travel decades before technology made it possible, filling notebooks with calculations about journeys that his contemporaries considered fantasy. His equation emerged from applying conservation of momentum to a vehicle that propels itself by expelling mass. The physics is elementary. The consequences are profound. The equation states that delta V equals exhaust velocity multiplied by the natural logarithm of the mass ratio. Written compactly, it fits on an index card with room to spare. Delta V represents the total velocity change the rocket can achieve. Exhaust velocity measures how fast propellant leaves the engine. Mass ratio divides the rocket's initial mass, fully loaded with propellant, by its final mass after the propellant has been expelled. The natural logarithm function makes the equation treacherous. Logarithms grow slowly. Doubling the mass ratio does not double the delta V. It adds only the natural log of 2, approximately 0.69 times the exhaust velocity. Achieving large velocity changes requires mass ratios that climb exponentially while delta V increases only logarithmically. The relationship punishes ambition with mathematical certainty. Consider what the equation means for practical rocket design. A rocket with exhaust velocity of 4.5 kilometers per second, typical of the best hydrogen-oxygen engines, needs a mass ratio of 2.7 to achieve 4.5 kilometers per second of delta V. Roughly 63% of the initial mass must be propellant. This ratio is achievable. Modern upper stages routinely meet it. To achieve 9 kilometers per second of delta V, twice the exhaust velocity, the mass ratio must climb to 7.4, roughly 86% propellant. Still achievable, but increasingly challenging. The dry mass fraction shrinks to 14%, leaving little room for structure, engines, and payload. To achieve 13.5 kilometers per second, 3 times exhaust velocity, mass ratio reaches 20 to 95% propellant. The rocket becomes a thin-walled balloon of fuel with engines and payload constituting barely 5% of launch mass. Engineering such structures pushes against material limits. To achieve 18 kilometers per second, 4 times exhaust velocity, mass ratio climbs to 55 over 98% propellant. The dry mass fraction falls below 2%. No rocket has ever achieved such ratios because the structural mass required to contain propellant and support engine thrust exceeds 2% of total mass before any payload is added. This exponential growth explains why rockets use staging. Rather than building a single impossible vehicle, engineers stack multiple achievable stages. Each stage provides a portion of total delta V, then separates to reduce mass for subsequent stages. The Saturn V that carried astronauts to the Moon used 3 stages, each optimized for its portion of the ascent. The first stage provided initial acceleration through the dense lower atmosphere. The second stage continued the climb to near orbital velocity. The third stage achieved orbit and later fired again for translunar injection. Staging extends the reach of chemical propulsion but cannot overcome fundamental limits. Each stage requires structure, engines, separation mechanisms, and control systems that add mass unrelated to propellant. Optimal staging for any given mission results in diminishing returns beyond 3 or 4 stages. Adding a 5th or 6th stage provides marginal improvement while multiplying complexity and failure modes. The round-trip Jupiter mission can now be examined through the rocket equation's unforgiving lens. Previous sections established the delta-V requirements for each mission phase. Launch to Earth orbit costs 9.5 kilometers per second. Trans-Jupiter injection from orbit adds 6 kilometers per second. Jupiter orbital insertion requires 1 to 2 kilometers per second. Operations at Jupiter consume roughly 1 kilometer per second for orbital maneuvers. Jupiter escape and trans-Earth injection demand 5 to 8 kilometers per second from practical parking orbits. Earth arrival and capture cost 1 to 3 kilometers per second depending on trajectory and aerobraking availability. The total round-trip delta-V budget reaches approximately 25 to 30 kilometers per second. Use 27 kilometers per second as a representative middle estimate for a mission without aerobraking at Earth return. Apply the rocket equation to this requirement using chemical propulsion with 4.5 kilometers per second exhaust velocity. The natural logarithm of the mass ratio must equal 27 divided by 4.5, which is 6. The mass ratio equals e raised to the 6th power, approximately 403. The spacecraft must start with 403 times the mass it will have upon completing all propulsive maneuvers. Propellant and expended stages must constitute over 99.7% of initial mass. The final spacecraft returning to Earth vicinity represents less than 1/4% of the mass that departed Earth's surface. These numbers describe a theoretical vehicle that cannot exist. No structural material allows building propellant tanks that weigh less than 1% of their contents while surviving launch acceleration and multi-year space exposure. No engine achieves perfect efficiency in converting propellant mass to thrust. No spacecraft design eliminates the mass of guidance systems, communication equipment, power generation, thermal control, and payload that a mission requires. Practical mass ratios for chemical rocket stages peak around 20 for highly optimized designs. Achieving a mission mass ratio of 400 requires stacking multiple stages, each contributing a portion of total delta-V, while maintaining achievable mass ratios at each step. The staging mathematics improves the situation but cannot rescue it entirely. Consider an optimistic staging analysis. Assume 5 stages, each with a mass ratio of 3.5, comfortably within demonstrated capability. Total mission mass ratio equals 3.5 raised to the 5th power, approximately 525. Each stage provides delta-V equal to 4.5 times the natural log of 3.5, approximately 5.6 kilometers per second. Total delta-V reaches 28 kilometers per second, sufficient for the round-trip mission. But this analysis assumes perfect staging efficiency. Real staging involves interstage structures that connect stages before separation. Real staging requires separation mechanisms that reliably release at the correct moment. Real staging demands thrust structure that transmits engine force through the stack. These realities reduce effective mass ratio below theoretical values. Real staging also requires that each stage carry the stages above it. The mass multiplication works in reverse during analysis. Starting from final payload and working backward through each stage, a 1,000 kilogram return capsule atop 5 stages, with mass ratio 3.5 each, requires a first stage of roughly 525,000 kilograms. This figure excludes Earth launch entirely. The 525,000 kilograms represents mass in low Earth orbit before trans-Jupiter injection. Launching that mass from Earth's surface requires additional stages with their own mass multiplication. The total launch mass climbs into millions of kilograms, exceeding the payload capacity of any rocket ever built by factors of 10 or more. Multiple launches and orbital assembly could theoretically accumulate the required mass in Earth orbit. The International Space Station mass is roughly 420,000 kilograms, assembled over 15 years through dozens of launches. A Jupiter return vehicle would require similar or greater mass assembled on a tighter schedule to minimize propellant boil-off during construction. The assembly scenario introduces its own challenges. Cryogenic propellants cannot wait in orbit for years while components accumulate. Hydrogen boil-off begins immediately upon reaching orbit. Each month of assembly delay consumes propellant that additional launches must replace. The assembly schedule races against thermodynamics in a contest that thermodynamics eventually wins. In-space propellant production could theoretically break this constraint. If hydrogen and oxygen could be manufactured at Jupiter using local resources, the tyranny of launching return propellant from Earth would be broken. Jupiter's atmosphere contains abundant hydrogen. Ice on the Galilean moons contains both hydrogen and oxygen. Extracting and processing these resources could provide propellant without the mass multiplication of Earth launch. But in-space resource utilization at Jupiter requires infrastructure that dwarfs current space capabilities. Mining ice from Europa or Ganymede demands landing systems, extraction equipment, processing plants, and transportation to orbit. Atmospheric mining at Jupiter itself requires vehicles that can descend into the atmosphere, collect hydrogen, and return to orbit. No component of this infrastructure exists. Developing it would require decades and hundreds of billions of dollars in investment. The solution to the propellant problem becomes a problem larger than the original mission. Chemical propulsion cannot close the Jupiter round-trip mission with any reasonable assumptions. The arithmetic forbids it. Mass ratios exceed structural possibility. Staging helps but cannot bridge the gap. Alternative propellant sources require infrastructure investment that exceeds mission value. The rocket equation permits no appeal. Nuclear thermal propulsion offers the most mature alternative to chemical rockets. The technology heats hydrogen propellant by passing it through a nuclear reactor core. The hydrogen absorbs thermal energy from fission reactions, expanding and accelerating through a nozzle to produce thrust. Exhaust velocities reach roughly 9 km per second, approximately double chemical rocket performance. The NRVA program demonstrated nuclear thermal propulsion between 1961 and 1973. Engineers at the Nevada test site built and tested nuclear rocket engines at various power levels. The engines accumulated hours of operation, demonstrating that nuclear thermal propulsion worked, that reactors could survive rocket engine operating conditions, and that the technology could eventually support human missions. Political and budgetary pressures terminated Nerva before any engine flew in space. The program achieved technology readiness appropriate for continued development but never reached flight qualification. The engines and test facilities were dismantled. The expertise dispersed. Nuclear thermal propulsion entered a decades-long hiatus from which it has only recently begun to emerge. Modern nuclear thermal designs could potentially achieve exhaust velocities of 8.5 to 9 km per second. Apply the rocket equation to the Jupiter round trip. With this improved performance, the natural log of mass ratio must equal 27 divided by 9, which is 3. Mass ratio equals E cubed, approximately 20. The mass ratio for nuclear thermal round-trip Jupiter missions falls within demonstrated staging capability. A 3-stage nuclear thermal vehicle with mass ratios around 2.7 each could achieve the required delta V. Total vehicle mass in Earth orbit might reach 50,000 to 100,000 kilograms for useful payload delivery. Multiple heavy lift launches could deliver this mass. The mission transforms from impossible to extraordinarily difficult. But nuclear thermal propulsion carries constraints that the improved mass ratio does not eliminate. The reactor adds thousands of kilograms to engine mass. Heavy shielding must protect crew from neutron and gamma radiation during engine operation. The hydrogen propellant remains cryogenic, subject to the same boil-off losses that plague chemical systems during the months of waiting at Jupiter. Nuclear engines cannot simply throttle up and down like chemical engines. The reactor requires careful startup and shutdown procedures. Emergency shutdowns may damage fuel elements. Restart after shutdown demands time for neutron poisons to decay. The operational flexibility that mission contingencies might require may not exist. Launch of nuclear materials through Earth's atmosphere raises safety considerations that have blocked nuclear space programs repeatedly. A launch failure that scattered reactor fuel across populated areas would create contamination requiring extensive remediation. Public opposition to nuclear launches remains intense regardless of technical safety arguments. Regulatory approval for nuclear space missions involves political processes that technical merit alone cannot navigate. The technology readiness for human-rated nuclear thermal rockets remains at level 5 or 6, indicating component demonstration in relevant environment, but not integrated system testing in space. Achieving flight readiness would require a development program spanning 15 to 20 years and costing tens of billions of dollars. No space agency has sustained such investment in nuclear thermal propulsion. The technology remains perpetually promising and perpetually unfunded. Ion propulsion achieves exhaust velocities that dwarf both chemical and nuclear thermal systems. Rather than heating propellant through combustion or nuclear reactions, ion engines accelerate propellant using electric fields. Atoms of xenon or other heavy elements are ionized by stripping electrons, then accelerated through grids charged to thousands of volts. The ions exit the engine at velocities reaching 30 to 50 kilometers per second, roughly 10 times chemical exhaust velocity. The rocket equation transforms under these conditions. For 30 kilometers per second exhaust velocity and 27 kilometers per second mission delta V, the natural log of mass ratio equals 0.9, mass ratio equals 0.9. Mass ratio equals e to the 0.9, approximately 2.5. The spacecraft needs only 2.5 kilograms at mission start for each kilogram at mission end. Propellant constitutes merely 60% of initial mass, rather than 99%. Ion propulsion appears to solve the Jupiter return problem entirely. Mass ratios fall within easy reach of spacecraft design. Propellant requirements shrink to levels a single launch could deliver. The arithmetic finally works in humanity's favor. The trap lies in thrust levels. Chemical rockets generate thrust measured in meganewtons. The Saturn V first stage produced 34 meganewtons, enough to lift 6.5 million pounds off the launch pad. Nuclear thermal engines produce thrust measured in hundreds of kilonewtons. These forces accelerate spacecraft rapidly, completing burns in minutes or hours. Ion engines produce thrust measured in millinewtons. The Dawn spacecraft's ion engine generated 90 millinewtons at maximum power. This thrust approximately equals the weight of a few sheets of paper resting on your palm. Dawn achieved its remarkable 11 kilometers per second of total delta V by firing its engine for years, accumulating velocity change through patient persistence rather than powerful impulse. The implications for crewed missions are severe. An ion-propelled Jupiter spacecraft would not execute brief burns, followed by months of coast. It would fire its engines continuously for years, spiraling slowly outward from Earth, spiraling slowly inward at Jupiter, spiraling slowly outward again for return, spiraling slowly inward at Earth arrival. Transit times extend dramatically. Rather than the 30-month chemical transfer, ion propulsion missions might require 4 or 5 years to reach Jupiter. The spiral trajectory through Earth's radiation belts adds months of exposure during departure. The waiting period at Jupiter, assuming the spacecraft eventually captures into orbit rather than simply flying past, extends mission duration further. Return transit adds more years. Total mission duration for an ion-propelled Jupiter round trip reaches 15 to 20 years. No human has spent 15 years in space. The record for continuous space flight is roughly 14 months. The physiological effects of 2 decades in microgravity remain unknown, but presumably severe. Bone loss, muscle atrophy, cardiovascular deconditioning, vision changes, and immune system effects would accumulate throughout the mission. The crew that eventually returned to Earth might be incapable of functioning in gravity. Radiation exposure over a 20-year mission would substantially increase cancer risk for all crew members. Cosmic rays penetrate spacecraft shielding continuously. Jupiter's radiation belts add acute exposure during the spiral, capture, and escape phases. Even optimistic shielding assumptions result in career radiation limits being exceeded multiple times over. Life support consumables for 20 years exceed reasonable spacecraft capacity. Air, water, food, and other supplies scale linearly with mission duration. A 4-year chemical mission might carry 40,000 kilograms of consumables. The 20-year ion mission would require 200,000 kilograms, consuming the mass savings that ion propulsion's improved mass ratio provided. The power requirements for ion engines compound these difficulties. Dawn's small engine required 2.5 kilowatts of electrical power. Engines producing enough thrust for crewed spacecraft would require hundreds of kilowatts or megawatts. Generating this power at Jupiter's distance from the Sun demands either nuclear reactors or solar arrays covering acres. Either option adds mass that erodes the advantages of high exhaust velocity. Ion propulsion solves the mass ratio problem, while creating duration, power, radiation, and human factors problems equally severe. The arithmetic permits ion-propelled Jupiter return. The physics and biology forbid it for crewed missions. The technology remains valuable for robotic exploration, where mission duration carries no biological cost, but cannot extend human presence to Jupiter. Fusion propulsion represents the theoretical ultimate in rocket performance. Nuclear fusion releases energy when light nuclei combine to form heavier nuclei. The process powers the Sun and all stars. If harnessed for propulsion, fusion could achieve exhaust velocities measured in hundreds or thousands of kilometers per second. Mass ratios for any conceivable mission would fall to trivial values. Jupiter round trips would become easy. Interstellar travel would become possible. Fusion propulsion does not exist. Achieving controlled fusion requires temperatures exceeding 100 million degrees Celsius, hotter than the core of the Sun. At these temperatures, matter exists as plasma, a gas of ions and free electrons that must be confined by magnetic fields, because no material container survives contact with it. The plasma must be dense enough and confined long enough for fusion reactions to occur faster than the plasma loses energy to its surroundings. These conditions have proven extraordinarily difficult to achieve. 70 years of fusion research have produced experiments that sustain fusion reactions for seconds or minutes, while consuming more energy than they produce. The ITER experimental reactor under construction in France will weigh over 23,000 tons, cost over $20 billion, and may achieve net energy production for brief periods by the late 2030s. It will never fly. Translating fusion from laboratory demonstrations to spacecraft propulsion requires solving problems that current physics cannot address. The reactor must be small and light enough for spacecraft integration. It must operate reliably for years without maintenance. It must direct fusion energy into propulsive thrust rather than dissipating it as waste heat. No design exists that accomplishes these requirements. No timeline predicts when such a design might emerge. Proposing fusion propulsion for Jupiter missions means proposing to wait for breakthroughs that may never arrive. The arithmetic of fusion permits Jupiter return. The engineering of fusion remains science fiction. Responsible mission planning cannot rely on technology that does not exist and may never exist. The hierarchy of propulsion options reveals Jupiter's position at the boundary of human reach. Chemical propulsion cannot achieve round-trip missions under any reasonable assumptions. The mass ratios required exceed structural possibility. Nuclear thermal propulsion could achieve the missions, but requires decades of development and political will that has never materialized. Ion propulsion achieves excellent mass ratios, but extends mission durations beyond human survivability. Fusion propulsion could solve all problems simultaneously, but exists only in theory. This hierarchy has remained stable for 60 years. Studies conducted in the 1960s reached the same conclusions that studies conducted today confirm. The fundamental constraints arise from physics that does not change. The gravitational constant determines how strongly Jupiter attracts. The binding energy of molecules determines how much energy chemical reactions release. The properties of plasma determine how difficult fusion remains. These constants set the boundaries within which engineering must operate. Some observers argue that transformative technologies will eventually overcome current limitations. They point to the rapid progress from the Wright brothers' first flight in 1903 to the moon landing in 1969. 66 years transformed aviation from a 12-second hop to interplanetary travel. Surely another 66 years will bring comparable advances. The argument misunderstands the nature of 20th century progress. The Wright Flyer and Apollo spacecraft both operated within the same physics. Lift equals the product of coefficient, air density, velocity squared, and wing area. Thrust equals mass flow rate times exhaust velocity. The equations governing flight in 1903 govern flight today. What changed was engineering capability to exploit those physics. Stronger materials, better engines, improved navigation, refined manufacturing. Each advance pushed harder against limits that remain fundamentally unchanged. Jupiter's gravity well is not an engineering problem awaiting better engineering. It is a physical reality that engineering must accommodate. The gravitational constant cannot be reduced through research. The exhaust velocity of chemical reactions cannot be significantly increased through improved engine design. The speed of light cannot be exceeded through any means known to physics. These limits define the playing field. Engineering chooses plays within the boundaries they establish. Chemical rockets already operate near theoretical maximum efficiency. Modern hydrogen-oxygen engines achieve exhaust velocities within a few % of the thermodynamic limit for their combustion temperature. Further improvement requires higher temperatures that would destroy engine components. The gap between current performance and fundamental limits has narrowed to the point where revolutionary improvement is impossible. Nuclear thermal approaches similar limits. The maximum exhaust velocity depends on propellant molecular weight and reactor temperature. Hydrogen provides the lowest molecular weight of any reasonable propellant. Reactor temperatures are limited by fuel element material properties. The 9 km per second exhaust velocity of advanced designs approaches the practical ceiling for the technology. The physics of the situation permits a clear statement: human round-trip missions to Jupiter remain beyond current capability. The gap between what is required and what is achievable spans factors that incremental improvement cannot bridge. Closing the gap requires either breakthrough propulsion technologies that may never materialize, or acceptance that some destinations lie beyond human reach. This conclusion carries implications that extend beyond mission planning. For the first time in human history, we've identified a destination we can see, study, and photograph in exquisite detail, yet cannot visit and return from. The moons of Jupiter reveal themselves to our telescopes and spacecraft as worlds with volcanoes, subsurface oceans, and geological complexity rivaling anywhere in the solar system. We can map them, we can analyze their compositions, we can speculate about life in Europa's ocean. We cannot go there and come back to tell the tale. Previous barriers in human exploration eventually yielded. The oceans seemed uncrossable until Polynesians, then Vikings, then Columbus proved otherwise. Mountains seemed unclimbable until someone climbed them. The sound barrier seemed unbreakable until Chuck Yeager broke it. The moon seemed unreachable until Neil Armstrong stepped onto its surface. Each barrier fell to human determination combined with appropriate technology. Jupiter may represent a different category of barrier. The determination exists. The technology does not exist, and physics offers no clear path to developing it. The rocket equation permits no appeal to courage, funding, or national will. The numbers work, or they do not. For Jupiter round trips with current and foreseeable technology, the numbers do not work. Accepting this limitation does not diminish human achievements in space exploration. Robotic missions have revealed Jupiter as a world of staggering complexity and beauty. The Voyager flybys transformed our understanding of the outer solar system. Galileo's 8-year orbital mission discovered evidence for subsurface oceans and witnessed volcanic eruptions on Io. Juno continues to probe Jupiter's deep structure and atmospheric dynamics. Europa Clipper will soon begin detailed investigation of that moon's ice shell and potential habitability. These missions succeed precisely because they do not attempt return. The mass that would be consumed by return propellant instead carries scientific instruments, communication equipment, and operational propellant for extended missions. The spacecraft achieve maximum science return by accepting that their journeys end at Jupiter rather than on Earth. Human exploration will continue to expand within the boundaries physics allows. The moon lies comfortably within reach, as Apollo demonstrated decades ago. Mars presents greater challenges but remains achievable with foreseeable technology development. The asteroids, some moons of Mars, and potentially Venus orbit all fall within the envelope that chemical and nuclear thermal propulsion can address. Jupiter lies outside that envelope. The round-trip orbital energy debt exceeds human payment capacity, using any propulsion technology that exists or can reasonably be projected to exist within coming decades. The gas giant remains a destination for instruments, cameras, and spectrometers, but not for human beings who wish to return home. This boundary may shift over time. Breakthrough propulsion physics, if such physics exists, could transform the calculation entirely. Fusion propulsion, if eventually achieved, would make Jupiter routine. Technologies not yet imagined might open paths currently closed. The boundary between possible and impossible has moved before and will move again, but responsible exploration must operate within current boundaries while hoping they expand. We cannot bet human lives on breakthroughs that may never come. We can only work within the physics we understand, pushing against its limits where they yield while respecting them where they hold firm. Jupiter holds firm. The arithmetic of the round-trip energy debt admits no current solution. The gravity well is too deep. The distance is too great. The propellant requirements too extreme. Spacecraft that enter Jupiter orbit remain there until they are destroyed. The physics that governs their fate would govern human missions equally. The gas giant hangs in our night sky as it has for billions of years, visible to naked eyes as a bright wandering star. Through telescopes, it reveals cloud bands in the Great Red Spot, a storm that has raged for centuries. Through spacecraft cameras, it shows moons that might harbor life, radiation belts that would kill unprotected humans in hours, and a gravity well that captures everything that ventures too close. We have reached across hundreds of millions of miles to study this world. We have sent our machines to orbit it, probe its atmosphere, and photograph its moons in stunning detail. We have learned more about Jupiter in the past 50 years than in all previous human history. We have not found a way to send humans there and bring them home. The round-trip orbital energy debt stands as a barrier that current technology cannot surmount. The arithmetic of forever continues to add the same sums it has added since Tsiolkovsky first derived his equation over a century ago. Jupiter waits, patient and immense, for technologies that do not yet exist to unlock journeys that physics currently forbids. Until those technologies emerge, if they ever do, the gas giant remains what it has always been, a world we can see but cannot touch, a destination we can reach but cannot leave, a reminder that the universe operates on scales and principles that human determination alone cannot override. The round-trip orbital energy debt is not a problem awaiting solution, it is a truth awaiting acceptance. We can visit, we cannot return. The journey is one way until physics provides an alternative. And physics has not yet provided one.